My name is Chen Xuelong, and this is my email. If you have any questions regarding the experiment, report, and marking, you can email me. I'm not very familiar with the still, and I may not answer all the questions you have, but at least we can discuss. So let's quickly go through the background. Steel is iron-carbon alloy with some additional elements. It is most widely used industrial materials. The range of structure and the property of steel can be achieved by controlled heating and cooling. The ability of heat-treated steel is connected with the phase transformation of iron. So by proper heat treatment, steels can be made soft or hard and strong. So with this experiment, you need to learn the heat treatment of steel first, and the effect of heat treatment on the mechanical property of steels. You need to test the hardness and the impact energy of steel. And at last is the effect of ionization of carbon on mechanical property of steel. So this image shows the iron-carbon phase diagram. The maximum solubility of carbon in austenite is 2% at this 1148 degree, and 0.02% carbon at this 723 degree. The equilibrium phase contains ferrite and cementite below 723. So in increasing carbon content, the strength increase, but the ductility also decrease. So let's see the several species of iron. The first is ferrite is the alpha phase of iron. It is a body-centered cubic crystal structure. The ferrite can transform into gamma phase of steel by heating at 910 degree, and the ferrite is soft. And the second phase, austenite, it is gamma phase of steel. It is a phase-centered cubic structure. Austenite exists about a critical eutectoid temperature of around 723 degree. And the third one, cementite, or we call it iron carbide. It is a orthotopic crystal structure. It can be formed by from austenite by cooling. And cementite is much harder but more brittle than ferrite. Perlite is a two-phase laminar or layered structure. It is formed when austenite is put below 723 with very slow clear rate. It is composed of alternating layers of ferrite and cementite. Martensite, it is a body-centered tetragonal structure. It is formed when austenized steel are rapidly cooled to a relatively low temperature. It is a plate or needle-like structure. So the quenching rate should be rapid enough to prevent the carbon diffusion to get the martensite phase. Martensite transformation is a diffusionless transformation. And the martensite is a hard structure in steel. It is strong. This phase is brittle, and the brittleness increases with higher carbon content, and it may lead to distortion of cracking. Add some additional elements can facilitate the martensite and moderate cooling rates. And Importantly, tempering is required to modify the strength and toughness of the monazite. So let's be familiar with some process of the heat treatment. The first is powder heating. Austenitizing temperature is the temperature to which the steel is heated in the austenitis to form fully austenitic structure. And austenitizing time is the time at the austenitizing temperature. Softer ferrite transform into harder austenite after this austenitizing. And quenching, which is you can call it rapid cooling. The quenching temperature is the temperature to which the steel is quenched from the austenitizing temperature. Quenching rate is the cooling rate during quenching. So if the cooling rate of austenite is very fast, monacitic will form with a large lattice distortion. And this is about the tempering. Tempering is a heat treatment due to brittle monazite. After this kind of tempering, quenched monazite, which is supersaturated current, transformed into tempered monazite, which is composed of stable, bright, and cementite phases. Tempered monazite may be nearly as hard and strong as monazite. And the tempering can increase softness, toughness, and ductility. Also can increase impacting distance, machinability, and malleability. It also reduces brittleness, hardness, and breadth. So the tempering time is normally around 4 hours. So after the heat treatment of steel, the grain size obtained depends on the diffusion rate of current. Slow cooling from austenite results in coarse perlite due to higher transformation temperature, and the faster cooling produces the fine perlite. The strength of steel increases with decreasing grain size and increasing cooling rate. And finer perlite is harder and stronger than coarse perlite. So the coarse perlite is more ductile. This image shows the hardness of monazite and perlite with function of carbon content. The hardness is a property of material which resists plastic deformation, bending, scratching, abrasion, or hardening. In steel, hardness increases with carbon content. Increasing carbon content will also result in decreased ductility and toughness. This two images shows the variation of hardness and toughness of the carbon steel with tempering, temperature, and time. The various combinations in hardness and toughness can be obtained by choosing the right processing conditions. So there are only two parameters in this experimental, that is temperature and time. So with high carbon content, steel possesses higher hardness, but also lower toughness after quenching and tempering. The decrease in toughness after tempering is associated with tapered monazite in embrittlement. We need to avoid this range. impact energy. So, impact energy is the energy needed to fracture material and standard definitions. We can measure the energy by the Harvey impact test. Also, you can measure the toughness of steel with different carbon content, different temperature and various temperature times. Large impact energy means higher toughness. And the test used to evaluate the ductile brittle transition temperature of materials. This is the experimental procedure. First, you will be grouped by A and B. Indicate the steel at some very high degree and pulling them into water, and you will temperature at 500 degrees with different durations. And then you will do the hardening test and the carbon impact test. Finally, is the report. For the results, discussion. First, you need to plot the impact energy and functional temperature time. Temperature time, and you also need to plot the HRC. What's the temperature time for both steels? Describe and explain the variation of impact energy with the treatment time. Also, the variation of hardness with the temperature time. And finally, you discuss the effect of current on hardness and strength of the steels. And I think your group need to submit a formal report. This is the format of the report. So if you want the picture. And this is how I will mark your report.
So just now can be our content page, is it? The content page of our report.
Yeah.
The previous slide.
Not repeat that. You need to follow this format.
No, I mean the previous slide. It can be our content page, is it?
Yeah.
For our report lah.
That means we follow that one.
Yeah, we follow the template.
We follow the
Yes.
sequence lah.
Yeah. Right.
it's good enough.
Kau buat lottery dapat 60 lah.
Yeah.
Betul. Tapi kalau graf longkang kan 40.
Kalau kau sosok mau ini so.
Yeah. Actually, you can follow this format.
Kira betul graf.
So that's it.
Kalau salah pun tak apa. Mesti dapat A.
Go je, don't scan. Jangan lupa hantar aku.
Okay.
Aku support
Okay,
kau.
there's one student haven't come. Everybody has signed, right?
Haven't come.
Okay.
Oh yeah, no more already.
Oh no more. No more.
Where's my thing? Oh, no more.
Ini dah stop belum? Kau dah stop.
Handsome lah this guy. Handsome siapa naik je.